Morning all for attending this morning. Hope everyone had a restful and fun holidays and happy 2025. Today we are very pleased to have Dr. Cameron here with us. He'll be speaking on a topic microcosm to macrocosm from sportomics to translational medicine. Dr. Cameron, he goes by Cam, is a biochemist who's very passionate about metabolism. He works as a scientific associate at the Schroeder Arthritis Institute, Krempel Research Institute, which is part of the University Health Network in Toronto. And over there, he's focusing on psoriatic arthritis and psoriasis at the present. In the past, he was a professor and principal investigator for the Laboratory of Protein Biochemistry, Center of Innovation in Mass Spectrometry at the Federal University of the State of Rio de Janeiro, and the principal investigator for the Center of Innovation in Mass Spectrometry at the Department of Biochemistry and Sportomics at the Olympic Laboratory of the Brazil Olympic Committee. He's one of the people who helped coin the term and research approach of sportomics, which looks at the application of metabolomics to investigate metabolic effects of exercise on individuals. For over 2 decades, he's worked as a doping consultant, collaborating with Brazilian and international athletes, engaging international courts, the World Anti-Doping Agency, and the Court of Arbitration of Sport Tribunals. He's published many peer-reviewed articles, book chapters, received many awards, and was an Olympic torchbearer in 2016. It's also famous enough to have a Wikipedia page, I realized when I was putting this together. His research interests encompass metabolic stress and translational medicine. He focused on bridging in-field N=1 studies to develop treatments for chronic diseases. And he has an interest in seeing if there is a way to collaborate and use some of the work he does in the cardiac world, such as in rehab or other areas. So that's part of the main reason for the visit today. So everyone, please joining me in welcoming Dr. Cameron.
Thank you, Vikas. Thank you for the invitation. And thank you, Lexi, for all the email trading and all the help to come here. So good because Calgary is not so cold as people used to say to me. So I'm enjoying the weather. Indeed, yesterday, Calgary was hotter than Toronto. Must be a record, but that's it. I'll try to do my best in this kind of hybrid conferences. So if you have questions, just let me know. I'll try to answer as the best of my knowledge. So let me here. So I don't have disclosure to do regarding this presentation. Okay. I would like to start with this very beautiful picture. And of course, it's a kind of difficult to read because that's about that's emerald plate. It was supposed to be written by Hermes Trismegistus. And Hermes Trismegistus was the father of the science that we call alchemy. So it was saying by Hermes Trismegistus, I need to be near to the microphone. So it was saying by Hermes Trismegistus that what's above is similar to what's below. Maybe some of you are trying to figure out why I'm talking about alchemy in a medical school, a medical university, or even in a biosciences meeting. But the interesting thing for me is that the ideas that people had in different perspectives can teach us a lot about how we can understand science. And I would say that I have some pairs that agree with me because the translation of this text as made by Sir Isaac Newton. So he was a person that was trying to understand what Hermes Trismegistus was trying to say long time before. So that's why I'm trying to bring the idea that we can, without extrapolation, because maybe some of you read the paper that was published yesterday or the day before yesterday in Nature, showing some proteins related to the sensation of loneliness. So people just evaluate loneliness in 45,000 people and try to relate with proteomics. And I think that that's a huge correlation to be sure about. Let's see what the future will bring us. But the idea is, can we bring a bridge between molecules and the big frame? That's my question here. So I would like to try to start about my original question. I was studying molecular motors inside neurons. So my question was about how molecular motors were proteolyzed by a protease, a physiological protease called calpain inside the neuron. So all of you are familiar with acetotoxicity glutamate induced. So when you have a moment of hypoxia or anoxia or even hypoglycemia, there is a input of glutamate into the synaptic cleft, leading to the opening of glutamate receptors. These receptors, they can open sodium channels or calcium channels, depending on the cell that we are talking about. So here you can see that AMPA and kainate channels, they open gates for sodium, while NMDA open for calcium, mostly. So depending on the kind of amount of these receptors that you have in the neuron, postsynaptic neuron, you are going to have a massive influx of either calcium or sodium, leading to the death of the cell. So we were investigating this and learned that when you have a massive influx of ammonia in the interstitium, you have a decrease in the recaptation of glutamate from the synaptic cleft, leading to an event similar to acetotoxicity. So we became interested in studying ammonia. And when I'm referring here ammonia, I'm going to refer to both states of ammonia, which is ammonia itself and ammonium, okay, just to make it easier. So just to remind you a little of your textbook biochemistry, most of the ammonia that we have circulating, they come from microbia. We have some contribution of ammonia that comes from the amination of amino acids. And also, we have another important way to produce ammonia that's a kind of forgotten, which is when you are using a lot of ATP for muscle contraction. So here we have this beautiful cartoon. As a protein biochemist, I need to tell you that this cartoon is wrong regarding the structure, but it's beautiful, okay? It's wrong, but beautiful and makes its job, which is myosin, in this case, is hydrolyzing ATP, so on and so forth. And the cell doesn't want to have a ATP-ADP ratio that's below the required amount. So one of the sources that you need to resensitize ATP quickly is to use creatine phosphate as a donor. That's the reaction catalyzed by creatine kinase to regenerate ATP. But there is another one that for some reason, it was a kind of forgotten in the biochemistry books, which is the reaction catalyzed by myokinase. Myokinase takes 2 ADPs to synthesize 1 ATP and 1 AMP. The problem is that you don't want to have a lot of AMP in the cell. And then you need to deaminase this AMP. And of course, when you deaminase AMP, you release ammonia. So that's why we jump into high performance exercise. Because during high performance exercise, you release a lot of ammonia. Just to give you some grains, if we measure ammonia here in ourselves, it's going to be between 30 to 60 micromolar. During acute exercise, it can reach 600 micromolar, even millimolar inside of the brain. So it's a huge amount of ammonia compatible with severe failure of liver, because that's the same that occurs when you have a liver failure. So that was my main thing, and that's why I jumped into sport, to try to understand how we can use athletes as a way to understand hyperammonic states, hypermetabolism. And then my lab in Rio, we shift to use mass spec as a tool to try to understand this problem, because in this way, we could do non-targeting analysis and try to use non-targeting analysis as a way to understand this problem. So I had the challenge of, at this time, to run 2 facilities with a lot of data, because we had since I had my lab in Rio, I was invited to build another lab at the Brazil Olympic Committee. That was nice because I built the lab from scratch, meaning from zero. I bought from the toe tip until the mass spec. So you can see that's completely like a fake lab because it was before the opening. But one thing that we did was, it's not about the lab. So if we want to understand athletes, if we want to understand what really happens with people, we need to go to real challenges. And athletes, when they are doing exercise training and competing, they are not doing that inside of a lab with controlled temperature, with controlled humidity, or whatever, or no wind. They are doing in real life. And our idea was, if we want to understand what is really happening, we need to go in the same place that the athletes are. So imagine that if you are going to work with Olympic sailors. So it's a kind of a challenge, but that was a typical experiment day for us. So that was a competition, a real world competition in sailing. And you can see here 2 Brazilian athletes. They are, this one with the gray suit, he won maybe 10 or 12 Olympic medals. And the other one, maybe less, 3 or 4, just 3 or 4. Yeah. But the thing is, we try to understand the challenge that they really lived. So how do we do that in a world competition? So we had this little boat that you're seeing here. We are not sailing, but it was a kind of this Navy SEALs boat. I don't know the name correct for, I'm not a marine, but we put all the things in the boat and we followed them and took samples during the competition on the sea. So they jump on the boat, give us blood, jump to the boat again and trade to the other one, as you can see here. So that was real life for us, for everything. So imagine that we were working with football players. So we need to follow the athletes in the games all over the world. In this case, we were taking samples in Switzerland before the Olympic Games in 2012 here. So the challenge was, we are trying to understand what happens with these athletes in real life conditions. And of course, that's a challenge. I can tell you that we were working with this athlete, and in this case, we were in Ukraine, in the middle of a game, in the interval between the two sets of a soccer game. And it was interesting because it was so cold that the machine froze. So we needed to use our coats to warm up the machine to put the machine to work. And then we're following him in Ukraine and after in Manchester United. And we have a lot of experience here. I'm showing you our room during the Toronto Pan American Games. You can see here some point of care devices, some dry blood spots. That what we used to do in Toronto was to collect samples using dry blood spot and send to mass spec in Mississauga, and having the results to give back to the athletes to the next day. So it was quite an operation. We did the same in Rio during 2016. You can see here a lot of DBS. And just to give you an idea, that's the amount of samples that we collect during the Olympic and Pan American Games. It's quite a few amount of samples. And we worked at different world multi-sport games. And the interesting thing is that for the athletes, what matters is not about metabolomics or proteomics or something like that. They care about medals. That's their policy. And one thing that was important to us is to bring them results that could help them to achieve better performance. And also longevity, because that was something that we were discussing yesterday in a dinner that was offered to me with very beautiful food. And the thing is not just about performance, but also about health. Of course, elite sports is not about health. That's another class of exercise. But trying to make the life of the athletes better and to make their living much more in sports, elite sports level. So giving you an idea, we worked with 102 athletes in 2016, and from this 17 Brazil medals, we worked with 12 of them. So I believe that we did our job helping them to obtain medals. And that's why we brought this idea of a concept which called Sportomics. Sportomics is the use of multi-omics science in order to understand sports. It's not to understand exercise itself, because we are trying to understand sports. So we are talking about an ex post facto science, exactly as you do here. You cannot put a person and, okay, can you excuse me? I'm going to burn you 70% of your body, and then I'm going to make measurements in you. You cannot do that. Of course, it's crazy. But if you have a person that had an accident, and then you can try to understand what happened. But it's the same thing. You cannot wait the person to have an accident. You need to measure things or to understand things after the fact. It's exactly the same thing. Or if you are analyzing petroleum, you cannot interfere in how the oil was made thousands of years ago. You just try to understand today. And I have a question to start this part of my talk, which is, we learned that that's life. Life is a bell curve. So we learned that 95%, that's the beautiful thing that make us happy. So the P of 5%, that's the best thing in life, and so on and so forth. The problem is, if your mother or your daughter is 0.0001% of population, she is 100% for you. Just have that in mind. And in my field, if we compare 100 meters running for 10 years, so this data is a little bit old because I just bring published data, okay? So here you can see we are comparing the first person during the Olympic 100 meters, okay, to the 10th person during the 100 meters. So that's the time. So we normalize by the first place, okay? That's why everybody here is 100%. And every color here is a different year. So you can see easily that during 10 years, and maybe I hope that somebody in the Zoom can answer me, who is the most rapid person in the world today? Everybody knows. Do you know? First. Huh? Correct. Who is the second? Did you need to think about? You can say the first. The second? Third. Tell me the third. So imagine, we are almost 8 billion of people in the world. You know the first, maybe the second, the third. And imagine the following. The difference, not between the first and the third, but between the first and the 10th is less than 2%. I'm not talking about the first and the second. I'm talking about the first and the 10th. And this data is reproducible for quick sports. In this case, we are around 2%. And if we go to the marathon, we increase a little bit. Now we are talking about 3 to 4% difference, okay? So the difference between the first and the 10th in the marathon is around 3 to 4%. And what happened with the first guy? He wants the gold medal, $1 million check, and a lot of girls or boys planning to dance with him or her. If you are the second, $30,000, and you not even know his name. If you are the third, you are going to need to pay your ticket back home. What I'm trying to bring here is that 5% in my life is useless, because we are talking about small differences. Bring to this audience is that we have differences that are among the 5% that we need to understand. So now I'm going to show you some results. That was a paper that we published a few years ago. So we had 30 players, football players, adults, semi-professional. Why we call semi-professional? Because these are the guys that are like they are the plan B for the team. So if a professional ones get hurt, they can bring the guys up for 1 game or 2 games or 5 games, and then they release back again. So they are a kind of spare, meaning they are extremely good, they play extremely well, but they are not real 100% professional. So we collect 8 samples. I'm sorry, I'm lying. 6 samples from them before game during 48 hours, during the game, meaning before, in the middle, and after the game, 1 hour after, and 48 hours after, correct? And then you can see here a non-targeting analysis of urine. So just to give you an idea, when we measure metabolites in urine, we are measuring around 3,000 to 4,000 metabolites. So that's the amount of data that we need to deal. And when we analyze this data, we are able to find some change in the xanthines pathways and the synthesis of urate. But I'm bringing that for you just as a way to tell you that what we were doing was just analyzing events that we didn't know what we are going to find. And a funny story here is when we were analyzing these things, the raw amount of metabolites, 3,000 or 4,000 metabolites. So here you can see the original table with the upregulated, downregulated, so on and so forth. So we found that 6 or 8 of the athletes were having sildenafil. So the question was, why these kids are having sildenafil? And after some interviews, we realized that they went to a party and they really had the drug. So the interesting thing here is when you are doing non-targeting analysis, you find things that you are not searching for. And how can we do that in science? So that was a paper that we published after the first one, when we analyzed the data. And in this paper, we proposed that this event, this soccer game, can lead to an increase in Hawkinsin. Hawkinsin is a metabolite of 4-hydroxyphenylpyruvate. So there is a disease called Hawkinsinuria, which is the inhibition of this enzyme, which is the 4-hydroxyphenylpyruvate dehydrogenase. So this disease is an inherited disease. And if a person born without this enzyme, he or she is going to have a huge amount of Hawkinsin, that's a metabolite in urine. So at the moment, we have 2 possible kinds for this disease. We have a brand disease that is mild. So we have the enzyme, but we don't process a lot. So the amount of Hawkinsin in urine is low. Or you have a severe disease when the Hawkinsin in the urine is high. So what we saw was we tracked that, and we found that these athletes, they had what we called exercise-induced Hawkinsinuria. It's not the disease. It's just something that appears because of the exercise. And also, we were able to show a lot of different shifts in the pathway for tyrosine metabolism. The idea here, of course, is to understand how can we use this data to understand both, or either way, the disease by itself, Hawkinsinuria, or even to understand tyrosine metabolism. It's needless to say the importance of tyrosine metabolism in different diseases, including Parkinson. So what I'm trying to bring here is that we have all these possibilities. Here, some data that we are uncovering now with canoeing. And I want to show you here that when we correlate different perspectives, so here we are correlating acute phase proteins and white blood cells presence, we can see by two different measurements that there is a signaling here. So you have together in this athlete C, you have a huge amount of correlation between the MPO, which is a marker for neutrophil destruction, appearing, and I cannot explain yet why, but the thing is it's showing something. The problem is we deal with a huge amount of data. Each square of that you are seeing here is a given data. And what we do together with Igor Jurisica is trying to do machine learning to understand the difference between the expression of these APPs, these acute phase proteins. Because here you can see we are talking about 98 athletes during 700 and some measurements, which means it's a huge amount of data to compare. And if you split the athletes regarding different sports, you can see that the correlation of the proteins is different. So each square that's hexagon that's red is talking about a pair of proteins. And this protein is regulated different here and here. Here, for instance, is SAA, and here is LBP. And doing this comparison, we can bring down different sports. In here, we are doing self-organizing maps for canoeing. And after having this understanding, we can talk with the coach and change the training for this given athlete. So that's the idea. We produce data, we bring data to the coach, and the coach changes the training. For us, we are trying to understand the mechanism. For the coach and for the athletes, what they want is medal. So that's what they want, to have medals and to win in different sports. So if we are able to deliver that for the athletes are going to be happy. And for us, what we need to understand again is what are the hidden metabolites that are appearing, why they are appearing. So just to give you a frame here, this was the case of Paulo Guerrero, because when you are doing doping analysis, you are searching for non-targeting molecules. So you're searching for molecules. And Paolo was found with a metabolite of cocaine, and we were able to show that he just had a T in Peru, because in Peru, what you are seeing here are different teas. So in this case, we have chamomile, and these teas, they are mixed with coca, because coca in Peru, Bolivia is completely legal. I'm talking about coca, the plant, not cocaine, the purified thing. But imagine if you have a machine that's able to find a very little amount of molecules, the machine is going to find the molecule and is going to say that the guy was having cocaine. So we did a lot of archaeological investigation, and we used hair to prove that he was not having cocaine, but instead of that, he had coca tea, a coca tea. And he was, at the end of the day, we were discussing that he was not completely unguilty because the court of arbitration in sport, they believe that as a Peruvian, he could be aware of the danger of drinking tea, but instead of 4 years, he just had 1 year. And if you want to see this story, you can see this series in Netflix. It's a very interesting story. Okay, but going to the end, the question is, what could we learn from Sportomics? So of course, the increase in performance to increase recovery rates, that's an interesting thing for the athletes, for the coaches. But what's the interest for us, for scientists? For me, is to understand and to reveal cellular and systemic responses to a hypermetabolic stress, which is exercise. And also to bridge what we learn in the bench to what can serve people in physiopathological studies. So here is some examples of that. Here we were doing a study in acute phase proteins in different sports. So here's the correlation between the different APP proteins. And we were able to build a protein-protein interaction map showing all these possible targets for inflammation during exercise. And the interesting thing here is that we can learn from this and bring this idea to other inflammatory states. That's why we did a different one here. And now we are starting to correlate not just acute phase proteins, but amino acids with the acute phase proteins in order to try to understand what's the relation between up and down regulation of metabolic, the metabolome in amino acids and the proteome in acute phase proteins. Because of that, my friends Vinod Chandran and Igor Juriska, they invite me to come to Canada. So I'm enjoying a lot the beautiful city of Toronto and now the beautiful city of Calgary. And the idea is, oh, that's the view from my apartment. That's the airport that we were discussing. And I took this beautiful photo of the tower here reflecting. So I came for the beautiful city of Toronto. That's where I'm working at UHN. And the idea is that how can I use what I learned from the protein perspective, which is extremely small into a cell, metabolism, proteomics, and sportomics, doping, and try to bring some help to the patients. And that's the new challenge. So I think that this challenge, at the moment, we are bringing this data to you that was produced, some of them by my crew in Brazil. You can see Max here. Max, I know Max for at least 30 years. And of course, the agents that give me the money, thank you very much, appreciate it. But to finish, I want to show you something that for me is being extremely interesting to discuss, which is, here I'm going to show you some unpublished analysis of 3 moments for 12 patients, okay? For surgery in the anterior cruciate ligament, okay? Because one of our colleagues there is. So we have before surgery, 2 weeks after, and 6 weeks after, okay? So what came from the metabolome analysis was that. So imagine these 3 points that we are seeing here, just give you an idea about the amount of the area of the molecules. So we are talking about 10 to the 7 of area. That's arbitrary units, just to give you an idea, okay? So these orange metabolites are some given metabolite, and the blue ones, another one, okay? We are talking about 2 different people. We look for this data, what would be the general idea of us? Okay, outliers, correct? So let's get. Remember the very first slide that I showed you? Not the very first, but in the beginning. Having sildenafil. They were young adults, but sildenafil was there. So when I had a nice look in this data, what were these metabolites? One was serotonin, and the other one was Ritalin. I mean, bunch of people was taking the one that was taking. They there are a lot of things that we can bring from non-targeting analysis. And maybe it's not a good idea to get rid of the outliers, because the outliers can be very interesting for us. And if you are thinking in the 5%, maybe you don't like outliers. I love outliers. But as usual, you must be extremely careful with new ideas, because new ideas can be dangerous, extremely dangerous. But who knows? As Carl Sagan said, I could be wrong. Thank you very much.
Let's see if there's any questions online. While we're waiting for that, I'll just make a comment. I found your 100-meter sprint difference is very interesting, because I think in cardiac care we're at the level of I would say maybe as high performance athletes as well, where we have multiple therapies to help reduce endpoints. The ones we usually care about, stroke, MI, and that. But new therapies probably only make an incremental difference because with what we have in our current understanding. So, if we have a new therapy that actually reduces the absolute risk by 2 to 5%, that would be huge. That's like a number needed to treat of, 20 to 50. So, so in our own way, we are sort of reaching points where, it's very little incremental changes we're looking for, unless something disruptive comes along where we make bigger differences. So, very interesting and, for us to sort of think about and look at, is there some of this we can use? There's a huge interest in personalized medicine in our, in our center. We have a precision medicine initiative that we look at incorporating some of these things as well. Any questions from the room? Sorry, go ahead. Yeah. So,
Okay, the question is, how can we assure that the protein or the metabolites that we are seeing is changing? The right answer is, I have no idea. But what I prefer to do is, if we have a baseline for this person, that's the real control for us. So imagine that we are following a person, exactly as this ACL data that I showed. We had 12 people that were not affected and one that was having serotonin or Ritalin. So imagine that we are following an athlete for 1 or 2 years. We build a baseline regarding this metabolite or regarding this protein. And then we can know that to this training or to this competition, the athlete is changing more than expected. If you are talking about how do we identify the protein or the metabolite, is a little bit different. To identify a protein, what we do is we proteolyze the protein and do sequencing in the mass spec. And regarding if we are talking about a small molecule, the way to identify is regarding to the mass to Z charge. Did I answer your question? Okay, the question is shortly saying, it's like, how do we understand the difference between the environment? Let's say the athlete is training in a high altitude or is having a different diet. It's impossible. The thing is, at least at this moment, I used to say that there is no, I don't believe in random process. It's just because we don't know the variant. That's the thing. If you study a little bit of cows, you know that determinist cows is about that. We didn't know the equations before the study of cows. So the thing is, the real answer is we don't know. We have a huge amount of variant, and we can try to understand, try to figure out, but it's impossible because imagine the following. Imagine that you have an athlete playing beach volleyball. So the surface that he or she is playing is uneven. So it's going to, let's say, bring much more tension from the tendons, and then the tendons are going to release, let's say, hydroxyproline in the blood. So is the hydroxyproline because of the tendon, or is because we need to try to figure it out, but at the moment, because of the huge amount of data, we need to try to understand, but to real ensure that it's impossible. That's why I always say that's an ex post facto science. So we cannot take out all the variants, like a diet, like a pill, like a bad night of sleeping, or if the person went to a party and stayed the whole night partying, because that's life. Ah, that's $1 million question. Yeah, indeed, that's the dream for everybody, which is, can you try to sort people regarding this science? So can we predict a good or bad performance regarding this? I'm afraid to say that my perspective is not. So what I can say is we have some outliers. We are just preparing a paper. Maybe we are 70 or 80% done, showing exactly this analysis that we are talking about in canoeing. We have 4 athletes, all of them super good, but we have one that's extra super good. So just to give you an idea, he has 2 gold medals, one in a short paddling, and another one in a long paddle, which means it's like being a 100 meters medalist and a marathon medalist at the same time. And this guy is completely outlier, but when you look the metabolism, it's just a little bit different from the others. So what I'm trying to say is not just about proteomics, not just about metabolomics, and that's why my thing when people try to put together, let's say, proteomics or metabolomics with behavior, or that's what I was trying to bring with this Nature paper. Maybe it's possible that we can identify with luck some metabolites that brings you to a depressed state. In this case, let's say serotonin, okay? But I would say that these metabolites, the dream metabolite, we can say that they are a few. And because we get badly used by glucose, because it was easy to us, high glucose, diabetes, low glucose, no diabetes. It was almost binary, almost, of course. But that's not true for the whole spectrum of metabolites, I think. No, they are a lot of difference, completely different, because depend on a lot of different things. Meaning, it's much more difficult than just say, okay, that's a number and you are above, below. And again, I think that we need to think that looking the whole map, the whole metabolome, not just one or two metabolites. But the standard deviation in an athlete depends a lot regarding about what he or she ate, rest, or so on and so forth. It's a challenge. It's not easy. But with time, you start to learn with this guy. That's the problem. You learn with this person. That's why I'm so fan of N of 1 studies. I think that in the future, we are going to have a lot of discussion in our science because, of course, in the past, we were depending on epidemiology because epidemiology gives you the perspective of what's possible and what's happened with a given population. But I believe that in the future, not for me, but for you, what you are going to see is N of 1 studies, understanding a person, understanding a case. And a near future, you are going to have a mass spec in your watch, believe me. And then the mass spec is going to tell you 100 metabolites in your Apple Watch.
What proportion of the Sportomic are
Oh, that's a good question. So I believe that there is a fair proportion of genetics, but being honest, I believe that the genome is just the recipe of the cake. So you need the ingredients, you need a good oven, and then you're going to bake a good cake. So I think that genetics, yes, they have a lot of influence, but it's not even close to the amount that we used to think about. Just give you an example. We worked with a golden medalist, and he won the golden medal in volleyball, and he's just 1.75 meters, which is extremely short for a volleyball player. But what he did during his whole life was, I will succeed. Of course, he had other performance that were able to counterbalance his low height. So I believe that's a bunch of things. Genetics is part of them, of course, but it's not even close to the amount that we originally thought about regarding sports. I hope that I answer your question.
We're at 9 o'clock, so we'll end the presentation. Thank you so much.
Thank you very much.
Thank you. Happy New Year, everyone.
Yeah.